So what I want to talk about is Wrangler, which is a tool for doing refactoring. It's a tool written in Erlang for refactoring Erlang programs. And you can use it. We did a survey when we started doing this project, which was a number of years ago. We did a survey of what the most used IDEs were for Erlang, and came up with the conclusion that Emacs was the most heavily used. And ErlIDE we've integrated with as well, but that was before IntelliJ was supporting Erlang. But you can also use the tool standalone. So you can call the commands from the command line or from the Erlang shell and still get refactoring that way. So Wrangler is a tool, but it's also a toolkit. As I say, it's usable from the shell and the command line. But what we have built inside, and I'll talk about this as the talk goes on, we've tried to build a language to make it easy for Erlang programmers to write their own refactorings. And we spent a long time worrying about what that would look like. And I think the reason that we spent a lot of time worrying about it was because we were trying to find one language for writing new refactorings, or one language for extensibility, whereas in fact what was lying under the hood were two different things. So we've produced an API for writing your own refactorings from scratch, and we've got a domain-specific language which allows you to script refactorings, simple refactorings, into more complex assemblies. And I'll talk about both of those things. And on top of that, we built a tool for doing API migration. So for example, maps came into Erlang R17. People had used dictionaries for doing similar things, so we built a tool that allows you to help migrate your code from dictionaries to maps. And also we built all using this API migration tool, allowing you to go from the old regular expression library regexp to the new one, RE. I don't really have time to talk about that. My talk I gave at the Erlang user conference last June. If you look at the video of that will talk about that stuff in detail. So Wrangler gives you that toolkit for writing your own refactorings. It's got that sort of extensibility built in. But also it's a tool set. So inside there, as well as being able to do refactorings, there's other tools that allow you to detect clones in your code. So you can detect when you've got duplicated code or almost duplicated code. It gives you ways of detecting that and eliminating that. I'll show you an example of that. And as well, ways of automating things that people want to automate, like frameworks for web services testing. And I'll say a tiny bit about that at the end if I've got some time. So it's been a platform we've used to do a number of things, and what I'll do in this talk is show you some of those in action. The one thing I wanted to do before I go into this in any more detail is to explain where the name comes from. We started off thinking, well, it's Erlang, right? And we're doing refactoring for Erlang, so we could call it Rerlang. But then we did a bit of I like doing crosswords, so anagrams came to mind. So if you do a little bit of anagramming, you get Wrangler, and if you stick a W in front, you get a real word. So that's where it came from. And a wrangler is somebody who can look after horses, who can tame difficult horses, or somebody who engages in a lengthy and complicated dispute. Some refactoring seem lengthy and complicated. Or it's somebody who gets a first-class degree in maths from Cambridge. So there's a nice collection of connotations for that. So let me explain a bit about what Wrangler is like as a tool. So the idea of refactoring is to change what a program does, but not to change how a program does what it does without changing what it does. And we see it as being part of a programmer standard toolkit. We saw yesterday in the presentation about IntelliJ, you could see there that it's one of the things that you can do as a matter of course. Some of the refactorings there for renaming and so on, you can just do as a matter of course as part of standard program development. And we provide things like renaming, function extraction, generalization, as integrated into people's standard programming workflow. And I guess refactoring is something that we do, but you want to have tools to help you do it. the phrase that people who advocate refactoring tools always use is that doing refactoring is tedious and error-prone. Doing it in practice, changing the name of a function throughout a project is something you can do with an editor, but you'll probably get some false positives and some false negatives. So you have to check all those instances to make sure that you're doing exactly the renamings you want and no more and no less. And you can easily make mistakes. So what we want to do is automate the simple things and cover the bureaucracy that it will be hard for you to do yourself in an editor off the shelf. And I guess one of the things that you realize quite quickly is that if you're doing this, you need to cover the whole language. You need to make sure you cover all of Erlang. You need to make sure you can cover a whole project. You don't want to refactor in a single file. And there's a rather vague question about where refactoring ends. So you refactor a project, but perhaps you better refactor the tests for that project. Perhaps you better refactor the make files for that project. Because if you start renaming modules, you better make sure that you rename them in your make files as well as in your tests and your project itself. So it can cover the whole project life cycle. And in something like IntelliJ, you've got advantages there, working within an IDE, which certainly will cover testing, and I guess will cover make as well. So you're getting all that. You're getting all that renaming within that closed world. Similarly with Erlang, Erl IDE. If you're working within Emacs, then you're pulling in tools of different kinds. Okay. Let me just show you a tiny bit about what we do, if this is going to allow me to do it. Let's have a look. Okay. So here we are we're in Emacs, and we've got a module here called ping pong. We can rename, let's have a look. We click on there. You can see Wrangler is a menu in Emacs. You can go to the menu, of course, because it's Emacs. You don't need ever to go to the menu because there are these beautiful runes that allow you to go straight to.
Can we make the font bigger?
I'm sorry?
Can we make the font bigger?
Which font?
The one in the text.
The one in the text, you can. The trouble, this screen is, yeah, we can do that. Just let me show, here are the menus, and as you can see, we're getting these beautiful runes here. Control-C, Control-W, that's the introduction for Wrangler, and then you get all the other stuff, which is how Emacs works, right? And RV for rename variable, RF for rename function. So let's rename this function. No, let's rename this one, actually. I'd rather rename this one. And you wanted the font bigger, John. Is that better? Okay. So let's rename the function. So you get the same. We're allowed to rename it. Let's call it init B. And of course, that's failed because we can't do that. It's already in scope. So we have to check. It's not simply a matter of doing a substitution. You can't rename it to something that's already in scope. But let's rename it to something that isn't in scope. Let's go back and call it IA. And we can preview this if you like, but let's just commit it. And you can see, for example, not only did it rename the function, rename that IA, it also had to rename it in a spawn, and it had to rename it in the export. Because you have to track the values of, you have to see that some atoms aren't just atoms, but they mean a function. So when you rename a function, you have to make sure symbolic calls to that function are also renamed. So you have to do that sort of analysis under the hood. And of course, if you did that with a text editor, it would simply rename, well, it might do okay there, but it could rename other things you didn't want to. And we can undo that. Let's just undo that refactoring. So we can go back to where we were. And of course, we could rename, if we wanted, what's this? The module's called ping pong. I could rename the module Let's commit that. And you can see that's changed in the spawn, and it's actually changed the name of the module as well. So we have to make sure, again, that we rename the things we want to rename, and we don't rename the things we don't. So it's built into Emacs and supports those beautiful runic command sequences, and also stuffs things into an appropriate menu. Let me move on. Go back to my presentation. Okay. And just for completeness, to show you that you can call this from the command line if you want to integrate this into other editors or do it outside an editor. And that's particularly the case for when you're doing batch refactorings. For instance, suppose you're changing the naming convention across a whole project, moving from camel case, where you have a capital letter inside a word, to inside an identifier, to replacing that capital letter with an underscore and a small letter. You can do that across a whole project for every name in the project. And of course, you probably want to do that outside an editor, and you can do that. Okay. So that explains what we can do by way of the simple sort of refactorings you see inside IDEs. What else can we do? Well, because Wrangler's written in Erlang, you're all Erlang programmers, so we can just say you can modify it however you wish. You can write your own refactorings using our beautifully crafted libraries. And of course, we say that and nobody uses them, because they might look a bit like that. So what we've tried to do is present a much clearer, high-level view of what Erlang, of what our tool can provide, and embedded in Erlang still, but hiding some of the details of what's inside our implementation. So it allows you to write extensions of the tool that much more easily. And you know Erlang. You're Erlang programmers, so we're quite happy with expecting you to be able to write Erlang stuff, but not having to know the details of, for instance, the way that the syntax trees are represented. It's not your job to do that. It's our job to hide that and to provide an interface so that you can extend things in the appropriate way. And as I said earlier on, I think one of the things that we tripped over when we first started thinking about this was trying to find a single language. So what we finished up with is providing two things: this API to define completely new refactorings from scratch. And we allow you to do that in Erlang concrete syntax. So we have a template language, which I'll explain in a minute, that allows you to describe Erlang syntax trees and so on using Erlang syntax. Concrete syntax, not abstract. So that allows you to write something entirely new. What we can also do is put refactorings together. So we can write scripts, which are actually rather more complicated than scripts, because we can control, we can generate whole sets of refactorings rather than forcing you to write down each refactoring. You can say, I want to rename every function which has this property, so an Erlang function that returns a Boolean, and I want it to be renamed using this Erlang function. So that's how we do things like the changing from camel case to Erlang identifiers with an underscore in them. So it's a sort of DSL, it's a sort of scripting language on steroids, if you like, but again, embedded in Erlang. So your Erlang expertise you can use to describe these particular transformations. And the sort of things people have asked us to do, this camel case thing I've talked about. We did some work for Qvik on instrumenting code in particular ways to avoid, when people at Qvik are writing models, they want perhaps to avoid certain behaviors in those models, and we were writing little transformations for them to do that. We've done work on API migration, of automating migration from an old library to a new library. Again, we've used this framework for doing. So what does the API look like? let me just give you an overview of how of a rationale for what we need to do. So what you see here is an example where, what have we done? We have generalized this function, body, over the particular message that's output there. So you select, if we're to automate this, if we're to use our API to do this, that turns into a parameter, and then at every call, we have to pass that in as an actual parameter to the call to the new function. So in order to describe a transformation like this, we have to be able to describe expressions in Erlang. We have to be able to say something like this head or something like this call gets transformed in a particular way. So we have to be able to describe expressions and how they are transformed. You can see those transformations going on there. But also you've got to describe the context in which this goes on, the context and scope in which that goes on, in order to verify certain preconditions. So for example, you can't generalize over something that contains one of the parameters to your function. Doesn't make any sense because that n is bound at from the parameter list. It doesn't make any sense to generalize over that. So you have to be able to check those things. So we've got to be able to build the API like this. We have templates that will allow us to describe particular expressions using Erlang concrete syntax, then rules that allow us to transform from the old form to the new form. We use the context to describe some preconditions, and then we have to describe a traversal about how the transformation is applied across a project. So those are the things that together give us our extension API. But again, all embedded in Erlang. Now let me explain a bit about what we've been doing more recently on providing support for introducing concurrency. There's a nice analogy about introducing concurrency. I don't know if anyone's a cricket fan. Perhaps not. I should have perhaps updated this to have a baseball game. But what you see here is the Oval in South London. It's a very calm, it's a very serene, very clear picture of what's going on. You've got a single cricket match going on there in the middle of this beautiful green pitch. Very nice, very elegant, but an awful lot of that pitch is not being used, right? You know, they've got, the action is going on there and there are people scattered around. If you go to Mumbai, there's a place called the Oval Maidan where people play cricket, and it looks like this. So there's one set of stumps, there's another, and there are about 30 cricket matches going on concurrently. It's complete chaos, but it works. So I guess the lesson here is that you get nice, elegant computations when you're sequential. If you try and introduce concurrency to get more performance, then your programs might get more complicated, and you need to think a lot harder about how you produce that. So what we've been doing is trying to identify parts of computations that we can perform independently, and base decisions on doing that, on doing what we call program slicing, what's called program slicing. We've worked on a tool called Percept2, an extension of Percept that's in OTP, that allows us to see what's going on within a particular application. And you can see here, these are 3 variants of actually our clone detection code. You can see that by making some transformations, by parallelizing parts of our code, we've managed to dramatically increase the amount of potential parallelism there is in that central processing phase and then in the final processing phase there. So trying to identify places where you might introduce concurrency and then introducing it. Now in practice, it can be, some things are easy. There's some low-hanging fruit. If you see a map, then you can turn that into a parallel map. Or if you see a list comprehension, you can turn that into a parallel map. But in practice, it often isn't like that. And so what we've tried to do is provide some support for a situation when it's not as simple as that. So what we tried to do is try and help you make transformations which fit in with an Erlang design philosophy. So working with OTP behaviors, perhaps turning synchronous calls to a server to asynchronous calls, and dealing in general with tail recursive functions and providing some sort of automation to support those things in Wrangler. So here's an example of the sort of thing we can do. You can say which part of the computation affects that, that part of the result. And that's effectively what slicing provides. And if you do it in this case, you'll see that the bits I'm highlighting in blue are the things that hit that. I mean, this is a particular regular thing. You might guess that you're doing something to two files, and the two bits of processing there are relatively identical. Now, what you can see here is that the computation of these things only requires the stuff highlighted in blue, so you can think of transforming what you see on the left into what you see on the right. So what we have done is replace the computation in line, do that and then that, with a spawn. The pink stuff is the boilerplate we need to add to support that, and we shift the blue computation into a separate process, and then we receive the result here. And that allows us to do those two pieces of computation in parallel. So that sort of, and within a single function. And we can do a similar thing here with turning a handle call where you respond to an asynchronous response from the gen server. So that's saying, instead of waiting for the result of that computation before you give the reply, just return the updated state and reply when you're ready, which I think was related to the things that Jose was talking about in his talk with things he's thinking about in Elixir, separating out bits of computation to do with state change, bits of computation that are pure computation. So separating out those two things from a gen server. And just to show you the change here, an example of what we do in the Wrangler API, how we support that. At the top level, we have a transformation that says what we're going to do is apply a transformation top-down to our code, and it's going to apply rule 1 when possible. And rule 1 is described like this. You can see that there are three aspects to it. You match the pink bit, replace the pink bit with the green bit in the case that the orange condition holds. And you can see that what we do is write the thing we want to replace in Erlang concrete syntax with some meta variables. So the Erlang variables that end with @ symbols are actually Erlang variables, but we treat them as meta variables, and that will match a sequence of Erlang variables. So however many arguments there are there, that args @ will match, and so on. So we can write in a familiar format. You don't have to know how we're representing things internally in order to see what's going on there. What we do here is the return result, and the side condition here is simply saying this is that you're refactoring the code that reflects the position of the cursor when you selected the transformation. And here you see what we do for in actually generating a new call. What we've done here is we do two slices. We do a backward slice from the result and from the state, and we find the things that are involved in computing the result, but not computing the state. So we have a list difference there. And this, from here, we're able to generate the new body of the function, which removes the expressions that, oh yeah, sorry, that's the body, yeah, and we, what's going on there? Oh, okay, those are the ones in the start-end location of there, yeah, that's right. So we get the new body like that, and then we generate, again, using the Erlang concrete syntax, we generate the replacement code, where what we do is using this template, we replace all the meta variables with the actual variables we've computed up there. So we're using Erlang as the meta language for doing these transformations. So if you understand Erlang, you can write these transformations. Okay, let me just show you briefly this slicing in action. Here we are. This is something from RabbitMQ. If I do what's Control-C, Control-W-E, if I select a variable and then do the slice and Control-C, Control-W-X. Oh, I'm not selecting an expression. Sorry about that. That gives us the slice for that particular expression. So that's showing that that particular component of the result, the member state 1, depends on this bit of code. It depends on the input variable state. But there are these other, this activity here is independent of the result that you're computing there. So potentially that's something you might float out into a parallel computation. So using this function slicing to provide you with hints about how to transform your programs. And you can see this, we could cover the whole, you can cover the whole expression here. If we select the whole expression, I guess we'd expect to see, oh, in fact, that activity isn't being used at all there. So that's intriguing. So, and this gives you a way of exploring your code in general. Whoops. Let's get rid of that. So plenty of other things to look at here. So there you can see that that internal broadcast, the pub count there, just depends on the state and not the message and the sizing. So you get that, you can see the dependencies within your functions. So let's go back to our presentation. Whoa, no, I didn't mean print. I meant that. How much time have I got? I can't remember what time I started. Have I got about?
Till 55, 4:55.
Okay. Right. An example here of handling a tail recursive computation, because typically Erlang computations are tail recursive. What can we do here to produce some more parallelism? What we've got is a computation that's entirely sequential at the moment. It looks like it's a tail recursion. What are we doing? We've got our termination condition is when we have an empty list. When we have a non-empty list, what do we do? We're computing on we're matching there on a variable that's 1. So we've got this number variable as well, which we're perhaps counting down on. And oh yeah, okay. So we're terminating either on empty list or having 1 there. So in general, what we do here is a tail recursion on this list here and this number here. And what can we do? What we would like to do is throw off as much computation as a separate process from this tail recursion. What are we doing? We're computing this group and this remain, and then some new groups, and then a new accumulator, and then calling the function again. So what's going on here? In doing this transformation, we work through a whole series of steps. We check, is the function tail recursive? We then have to analyze which of the variables is an accumulator, and then what we need to do is partition the body of the function in order to find out what part of the computation we can float out, what part of the computation gives us new values of the parameters, and what gives us a new value of the accumulator. So the sort of analysis we're doing, well, tail recursion, we do a syntactic check. That's not complicated. So how do we work out what the accumulator is? What we do is apply this condition. It will be a value that depends on itself and some others. It will be that no other parameter depends on its value, and its value is not used in the termination condition of the recursion. That's the way we characterize what the accumulator is. And if you look, remain has some of the other parameters. Remain is, what am I looking at here? No other parameter depends on its value. So if we're looking here, then the number of nodes there, other things do depend on that. So remain is a candidate but gets thrown out for that reason. This parameter gets thrown out because it's used in the termination condition, but this parameter meets that condition. So we can see that the final parameter is potentially an accumulator. And then we can ask, what can we float out? What we want to do is float out from the things that the accumulator depends on, those bits of the computation which don't depend on the value of the accumulator and don't overlap with slices of other parameters. So these are the things which we can compute separately and which don't affect the other parameters. And so the thing that we find we can float out from here is this new group computation. That's the thing which is being done independently of the other things, so that's something we can float out. And we produce what looks like a horrendously complicated piece of code, but what we do is effectively put inside let me leave that. Put inside a piece of worker, right, that comes automatically. Inside a whole lot of template code, we've got the 4 lines which made up our original body of our tail recursion. All the rest is dispatching values off and collecting the results in an appropriate order. So what we've done is make this whole thing more parallel, make it substantially more efficient by transforming that original function body into what we see here. And that we can do entirely automatically. Now you might ask, that looks absolutely horrendous. Why on earth would I put this into my code? Why would you make a transformation like that explicit? I think the answer is that this is a step that's part of your explicit development. You've decided you want to make your code more efficient, so you better put that into your repository. Put that step in your repository. Could you just do that inside a compiler? Well, maybe, but compiler-based transformation is notoriously fragile. You can't be sure that the compiler will do exactly what you want. So it's much better to make that transformation, put it in your repository. If you don't like it, you can always undo it. But I think putting that in there explicitly means that you know precisely in your development cycle what you have done why you've done it, you'll document it, and you've done it in an entirely automated way, which you can undo if you want to. API migration, I won't say anything about because I talked about that at the EUC last summer. That's all in my talk from there. But let me say a tiny bit about Wrangler as a tool set. One of the things that we've implemented and we use quite widely is, we've used particularly in looking at cleaning up test code, for example, is clone detection. So for example, you can see here, it's actually a similar code to my demo code. Let me show you this in a demo, actually. Let's escape. Let's go into my demo code. Here we are. Let's go back to this ping pong. I'm going to make it a tiny bit smaller, John. I hope you don't mind, to allow us to do a bit of clone detection. You can see here, these two pieces of code look pretty similar. Let me see what our clone detection will do. Let us. So we can go into similar code detection. We've got a number of flavors of this. I don't have time to go into the details of this completely. You can do a search across a whole project for similar code, or you can search within a single buffer. I'll do the latter just now. You can do it in a completely undirected way. We can say, just find us all the code that might be similar. So you're doing that as an initial step, but then you can focus in and say, I want to find everything similar to this. So you select an expression, and then you can find everything similar to that particular expression. But let's go for the similar code in the current buffer. Now, there's a question about what similar code means. Of course, there isn't a default definition. There isn't a black and white definition of what similar code is. It's parameterized on a number of different dimensions. I'm going to, because this is a small example, I'm going to say it can be one expression or more. It can have a tiny number of tokens. You can parameterize it on the number of times that code appears. Let's say, let's just say 2 here. You can parameterize it on how many ways it can be different. Because what we're doing is looking for similar code. When things are different, when there are differences in two instances, they'll get replaced by a variable. How many variables do you want to introduce? Well, let's say 4 as a maximum. That's our default. And then finally, some sort of similarity score. Because this is small, that measures the size of the code, the generalization of all these instances to the instances themselves. Let's just say 0.2, though I think the default value would work here. And, oh, it's told us similar code detection has finished, and we're told, let me just move this down, we get a report of all the clones we found. Okay, if you run this on a largest project, you might get 40 or 50 clones. Of course, this is a tiny file, we're getting 1. But what you see is a report that tells you where the code occurs. It tells you how it's parameterized in each case, and it gives you a report. So I can click on these. This is the equivalent in Emacs of a nice clickable list in something a bit more 21st century. So that shows us where we get where we have our instances, and then we can replace these. What we do is take the new definition. Okay, that is a bit clunky, I agree. And we just stick it in here at the end. Let's paste that in. So now we have our new function. Now, what we can do using our DSL, we can, let's go to refactoring, general, here we are, batch clone elimination. So we've got something that will help us eliminate clones from, oh yeah, so let's save that. Now, the interesting stuff is happening in that buffer at the bottom. What it says, first of all, is you've introduced the common abstraction for all these clones is called new fun, because of course what else would it be called? You can't work out what it's going to be called, but I'm going to call it loop. So it says, do I want to rename it? Yes, I want to call it loop. Okay, so it's renamed that, and now of course it's introduced these new variables, and I'm prompted for renaming all of those. And what should we call those? Oh, that's a message, so let's call that message 1 or MSG1. What's the second variable? Oh, that's there, that's a string, so let's call that string. New variable 3, what's that called? Where's that? Oh, that's a process, so let's call that PID. And what's new variable 4? Oh, it's another string, so let's call it string 2. String 2. Okay, now it says, oh, do you want to swap the parameters? Well, do we want to swap the parameters? No, I think I'm happy with those. But we might want to change the order. Oh! Please answer yes, no, right. What do we want to do? Now, let's say yes. Now, what this is doing is running through all the instances, and it's saying, do you want to replace this instance with the new function that we found? So let's say yes for that. Oh, and what this has done is you can see that it's replaced those two instances with that call to the new function. Now, what was nice is that we've used the domain-specific language under there to put together renaming of functions, renaming of variables, replacement of a function body by a call to the function, and put that together into that single refactoring called batch clone elimination. And so we've got that. But if we decided we didn't want it, oh, no more history to undo. Oh, help. Right, well that's something funny happened there, but we could in principle replace that with, yeah, what happened there? Oh, never mind. I don't know why I got all those dictum, oh dear, something peculiar has happened in there, but never mind. We got all these dictum outs. No, let's cancel that. Okay, but you can see what's going on there with the clone detection and replacement. Let me get back to my talk and let me finish. So you can see here, I've run through precisely that. We renamed the function and the variables. We didn't reorder the variables. Oh, add to the export list and then fold it against the definition. So we did all that. You've seen the demo. You can see we didn't just have, it's not simply a script. When we do, when we use the DSL, we have to deal with, for example, if something changes its name, we have to be able to access the new thing by the old name. So we have to track changing names and positions. We deal with generating commands and not simply specifying commands. We also have to deal with the transactionality of refactoring. So for example, if I'm doing a sequence of refactorings, in some cases it doesn't matter if one of those fails. So for example, if replacing the body of a function, or an instance of a function body by call to the function fails, that doesn't matter. We just leave the code as it is. But there are other situations where if we're trying to rename a function and we can't rename every instance, then the whole refactoring should fail. Because unless you rename everything, you'll change the semantics of your program. So some composite refactorings should be treated as a transaction, others shouldn't. And we allow the user to control that. So it's not simply scripting, it's scripting in a domain-specific language. And you can see, for example, in clone detection, we call the transaction an atomic refactoring, if you like. We say at the top level, all of these things must pass. So we must be able to rename the function, rename all the variables, do all these, but within replacing instances of the clone, if one of those fails, it doesn't matter. We don't treat that as a transaction. So we've got that nice control over non-transaction this particular part is non-transactional, but the whole thing is a transaction. Okay. And we get leverage out of embedding this in Erlang. So we have the embedded DSL here. For example, we can use this macro. This allows us to use the old name, MFA, for whatever that function is called currently after some renaming. We can call user input. This describes a refactoring. So the DSL stuff is pink, but we're using Erlang constructs within that. So we're using the fact that we've embedded that DSL in Erlang to give us the power there. Yep, okay, and I am not going to talk about WS Toolkit beyond saying what it allows us to do is automate a whole lot of stuff for doing web services testing. So we can use this as a way of generating code, and in fact generating refactorings for evolving that web services testing code. I wanted to say, because say many thanks to Hui King Lee, who did work on this with me for a number of years. She's now doing all sorts of horrendous refactorings and so on for a large telecoms company in the UK. But you know, I'm very, very grateful indeed for all the work she's put into this over the years. And we're very happy to have involvement and collaborate with people. This is where you can, this is our repository where you can get Wrangler and some of the other things we've been working on. And I also want to acknowledge support from these 2 European projects. So that's it.
I guess we have time for one question.
Okay.
I was curious,
Yeah.
what do you use to parse all the Erlang?
So we use the Erlang parser. Okay. So we've not written our own parser. Okay. Because then, you know, every time you write something yourself, you have to maintain it. Mm-hmm. And so that's a problem. So what we aim to do is recycle as much as we could from the Erlang tool chain. Mm-hmm. Now, the disadvantage of that is that you have to work around what other people have done, though the Erlang parser is very nicely extensible. So we can put things like source code information, source code location information, and so on into that. But if you work with your own parser, then you know, you have complete control over what you're doing, but you have to evolve it every time Erlang changes. So when maps come in, you have to include those. You have to process macros in the same way. So you have that sort of overhead. Mm-hmm. So there are advantages and disadvantages.
Mm-hmm. Right, thanks so much for talking.
Okay, thanks.